Yes.
Perfect. Um, Welcome everybody to the third tutorial. Hyukjae, you can go ahead and share your screen. Um, the first thing is some housekeeping reminders. The first reminder is the two-page proposal is due on June 15th. Those two-page proposal includes your um, it's just a basic proposal you guys can put up. We're going to just simply evaluate it and see if teams are being serious. And there's no very rigorous way of having to the formatting of the proposal here. But we want to see what the ideas team are coming up with. So that is due on June 15th. Hopefully teams can use this tutorial series to have generate some type of idea, innovative idea for their uh, projects themselves. And for the if you may want to check the change of timeline or anything, please go to the GitHub page, which is written down here. The GitHub page has a live update on everything, all the timeline changes and all the deadlines that we are having. So I believe the recording is in progress already. Today's topic, we are going to talk about the specifics of, well, after you have a foundation model, right? How do we evaluate the model and how do we evaluate it as a sort of a foundation model? And so today, Hyukjae will mainly focus on um, the keys of evaluating a model. How does a model fit the criteria foundation model here? What are the evaluation criterias we're going to have? And what may the test evaluation look like for your later test evaluations that we're going to provide? So we're just going to merely provide an example. The example is going to be provided on both of the GitHubs, the original MagNet X GitHub, as well as the MagNet Challenge 2 GitHub. And these simple examples will give you a glimpse of what we have decided to do to evaluate our models. And does not have to be what you guys are going to do, but it simply provides an example to start. So you guys can use that and play with it and figure out the way that your model can be used to be evaluated. So without further ado, I'm gonna hand it over to Hyukjae.
So Shukai, one more thing. Sorry, it is a little bit loud on my side. So the rules that we're presenting today is actually more or less what we're going to do in the final evaluation. So Shukai mentioned that no, everyone use your own way. No, it's actually we most likely will use the method QJ is presenting to evaluate your models at the end.
That's correct, yes. But the model itself, the model we're using today is an example. But yes, the testing data, the format of testing and everything will be more or less what we're going to do for the final evaluation. So yeah, go ahead, Hyukjae.
All right. Thanks, Jakai. Uh, can you hear me right? You can. Yeah,
Yes.
sure. Hi, and welcome to tutorial session 3. I'm Hyukjae Kwon, and today we'll be discussing the model testing and evaluation rules for MagNet Challenge 2. Before we dive in, let me briefly reintroduce the foundation model used in this challenge. This model architecture is mandatory for all participants as it defines the standard testing and evaluation framework. The core idea behind the foundation model is to read historical magnetic behavior and predict future responses based on incoming inputs. It is designed to provide the reliable predictions regardless of their frequency or time steps. Also, we hypothesize that the impact of initial state has finite time horizon. That means it should converge over time to steady state conditions. Also, the model should be flexible and accurate and adapt to any arbitrary excitation waveforms. So when you build the models, you have to follow those rules. Yeah, so when you build a model, the outcome should be a callable prediction function. That means the output future H should be determined as a function of past B and H sequences, along with the future B sequence. As mentioned earlier, the model must provide accurate predictions regardless of the length of past and future sequences. So, how can we build a model that predicts an entire future sequence? Here's an example model we use in this tutorial. It's an LSTM-based model that takes 80 time steps of past B and H as input, along with the next scalar value of B, and outputs the corresponding scalar value of H. You might see here that we are using the memory sequences of B and H sequence, and also the next point of B, the scalar B value, and it goes to the neural network and outputs the scalar value of H. Now, let's say we have a target sequence prediction here that we want to predict. In this example, the green section represents the non-input values, while the orange section indicates the unknown output values we aim to predict. Given the memory window and the next B value, the model can predict the next point of H. However, this only gives us a single point. So the question is, how can we extend this to predict the entire future sequence? Well, the autoregressive prediction is the key. Instead of predicting the entire sequence at once, we predict the one point at a time. Once the model predicts the next point of H, we treat that predicted value as part of the input for the next prediction step. This process is repeated. Each prediction becomes the input of for the next until the entire sequence is generated. So as you can see here, the memory window shifts forward to include the newly predicted H value, and the model then uses this updated window to predict the next value, and so on. In this way, the model builds the future step by step, just like how we might forecast weather based on today's data and each new day's estimate. However, in this example, we assume that the memory window size defined by the model is the same as the input length. Well, this is just an ideal case. In practice, the test dataset may contain input sequences that are either longer or shorter than the memory size. Since the model must handle arbitrary sequences, it should still function properly even when there is a mismatch between the input length and the memory window size. In addition, there might be differences in sampling frequency between the model and the test dataset. While our model is trained with a 60 MHz sampling rate, the test dataset may have a higher sampling frequency or lower sampling frequency. So how can we deal with these mismatches? We've included the code to address these issues. First, if the sampling frequency of the test dataset differs from that of the model, for example, if the model sampling frequency is higher, then we upsample the test dataset to match the model sampling rate. Conversely, if the model's frequency is lower, we downsample the test data accordingly. This ensures that the input format aligns with the model's expectations, maintaining prediction accurately. Well, this code handles the case when the sampling frequency of the test dataset is different from that of the model. You can find this code on this GitHub repository. In this code, told, you can see the TB old and TH old here, represents the original time axis based on the test data sampling frequency, while the TNew is the rescale time axis corresponding to the model sampling frequency. For example, in this tutorial, it should be 60 MHz. Each B and H sequence is then interpolated onto this new time axis to ensure alignment with the model. If the sampling frequency already matches, then interpolation is skipped and the original data is used directly. Now let's look at the another case, when the total number of time steps differs from the model's memory window size. If the input length of the test data is shorter than the model's memory window, we fill the remaining time steps with the initial value of the test data to preserve the continuity. On the other hand, if the input length is longer, we simply take the most recent time steps up to memory size. This ensures that the model always receives the correct input size it was trained with, regardless of the original sequence length. So you can see the code corresponding to different time steps. This is the code that handles the differences in time steps between the model and the test dataset. As shown here, if the model's memory length is longer than the input sequences from the test dataset, we pad the beginning with the first value of the data. If the test input is longer, we simply select only the most recent values. Here in this code, the B feature is created to provide the future scalar input of B. And H feature is the corresponding ground truth used only for the evaluation. And the B sequences and H sequence represent the past B and H sequences used as the memory window inputs in the model. So using those codes, we are now able to handle differences in both sampling frequency and memory window length in the input data. Now let's look at the testing dataset for evaluation. Well, I guess this would be the most important part of today's session, right? So what we provide for test is speed, age, and temperature data. Each sequences consists of 1,000 time steps, and there are 105 sequences in total. These sequences cover 7 different frequencies, 3 temperature levels, and 5 different input-output ratios, such as 90% to 10%, 70% to 30%, and so on. For now, we've distributed the 3T90 test dataset, but test datasets for the other materials will be available in few weeks. Note that the test data is randomly sampled from the release dataset. So in some cases, the model might perform slightly better because it might have already seen similar patterns during training. If you'd like to evaluate your model on unseen data, you're welcome to create your own test dataset using data outside of the training set. But for the evaluation, we'll use our own test dataset to evaluate all of your models. For the full code, please visit the MagNet Challenge GitHub repository. For now, the code is available at the link shown below. So now let's look at the testing results of our tutorial model. These plots show the results of H sequences predictions. In each figures, the red represents the predicted H values, and dotted blue shows the major ground truth H sequence, and dotted gray here represent the input memory of H used by the model. In the upper figure, the test conditions are 200 kHz, 50 degrees Celsius with a 10% to 90% input to output ratio. The lower figure shows results under 500 kHz, 70 degrees Celsius with a 70% to 30% ratio. As you can see, the model performs reliably across varying memory length, frequencies, and temperatures. This figure shows the NRMSE for each of the 105 predicted H sequences. As you can see from the histogram, the average prediction error is approximately 16%. In addition, we also computed the average NRMSE group by sequences with the same memory length. These results would provide you with further insight into how prediction accuracy varies depending on the input memory size of your model. The other evaluation criteria is the energy loss computed by integrating HDB. Here, note that since the 1,000 time steps do not form a full hysteresis cycle, the loop is not closed. Therefore, the result cannot be interpreted as the total code loss, but rather as the energy loss over the given time interval. For this evaluation and for this model, the NRMSE is approximately 40%. To conclude this tutorial session on evaluation rules and testing datasets, the key objective is to develop a model that generalizes well across different magnetic materials, excitation frequencies, and input memory length. The model should take past B and H sequences along with future B sequence and accurately predict the future HT. Evaluation will be based on the predict the future HT. The prediction accuracy, for example, like an RMSE value of H sequence, and energy estimation, and model complexity in terms of the number of parameters. Now let's take a closer look at the evaluation code. When you visit the GitHub repository link here, you'll find the tutorial 3 folder, which contains the testing H5 files, the main evaluation script, a sample model, and the normalization parameters. The 3C19 testing padded H5 file provides the input sequences of B, H, and temperature data. It includes 105 sequences with varying past and future lengths. The 3C90 testing truth file is not used for inference, but serves as the ground truth H sequence for evaluation. The Jupyter Notebook is the main script used to evaluate the model's performance. We will walk through in detail soon. The included model is the example LSTM model introduced earlier. The normalization parameters were generated during the training processes and are required for consistent data scaling. Lastly, the output folder will contain the predicted and measured H sequences generated during evaluation. This is the end of the slides, and we'll go over the codes of the Jupyter Notebook as I mentioned. So you can find the code in the GitHub repository, and this tutorial demonstrates how to test the model. For here, we use the LSTM model for the sequence to scalar future hysteresis step predictions. As I mentioned earlier, the test data set consists of the seven frequencies, 3 temperature levels, and 5 different combinations of past and future lengths, totaling 105 sequences, each with 1,000 time steps. So at the beginning, you have to import the packages, like important packages for the testing, such as like this. And then you have to define the network structure, which is the same model that you used in the training sessions. It should be the model that you have used for the training. So we use the LSTM model based encoder projector decoder neural network model. Now let's walk through the get data set function, which is the key part of our evaluation pipeline. This function prepares the testing dataset to match the format expected by our model. So this function takes in the B, H, and temperature data and the ground truth of the H sequence data from the test set, along with the test sampling frequency and model's expected sequence length. So at first, we load the normalization parameters here that were saved during training. And we extract the normalization parameters, something like average value and acidity value of each sequences. And then we calculate the test sampling time, the frequency of test data sets, and total time of B and H to keep consistency with our model. And you can see the model's internal sampling parameters for our model is 60 megahertz. So the time and frequency is set is like this. Then this is the same as I introduced in the slides. So this part of the code prepares the input format expected by our model. So the T old represent the original time axis on the test data set sampling frequency, while T new is the rescale time axis corresponding to model sampling frequency. And you can see the B and H is the past sequences of past sequences, and H true is only for using for evaluation, which is the ground truth values for the H sequence. And then each B and H sequence is then interpolated onto this new time axis. You can see here to ensure alignment with the model. If the sampling frequency already matches, then we don't have to interpolate, and we can just use the original data directly. And then we go through the time state differences to adjust the length of the sequence if it is different from the model inputs. So if the window size, for our example, we are using the 80 steps. So if it's longer than 80 steps, let's say like 200 steps, or if it's shorter than the 80 steps, like for example, like 50 steps, we make it consistent, like all them to be 80 steps, 80 time steps. Since the model requires the 80 time steps, if the model's memory length is longer than the input sequence from the test data, as you can see, we are padding the beginning value, which is the B sequence, the 0 value, with the first value of the sequence. And the path length is determined by the difference from the model data length and the testing data length. If the test data length the test input is longer, then we simply select the most recent values here. Oh yeah, so and this part is the input format expected by this part created the input format expected by our model. So since the model requires 80 time steps of the past B and H sequences, along with the scalar value representing the next B point as input, we construct them accordingly. So this B scalar value stores the scalar future B inputs. As you can see, the B future, the first value of the B future, and H out is the corresponding ground truth H values for the evaluation. And in B next is the shifting window of ATB values that moves forward step by step, forming the time series input for H predictions. Then we, in this for loop, we vertically stack these inputs to create a batch of prediction samples. Each row in B, in H, you see here in B, in H, B scalar, T scalar, and H out corresponds to one prediction step in the sequence. This batching allows the model to perform multiple forward predictions efficiently, simulating autoregressive prediction across the whole sequences. Then we normalize all inputs using our normalization parameters. And we also store the normalization stats for each sequence for inverse transform. Then we convert to the PyTorch tensors to use it in our model, train the model. And you can also use the plotting for visual check. We just use the B and H true value if the model gets the correct input values. The next is the testing the model. The next step is the testing the model, and This function returns the number of trainable parameters of the model, so it shows how many parameters you used in your model. And this function, as I shown in the evaluation criteria, it computes the total energy. So energy density over time using the trapezoidal rule for integral h dB. And this is the main test routine. It takes the test dataset, runs the model, and returns the predictions. We locate where future values, starting using the NP is NH. These non-values indicate unknown H, which is the future H sequences. And then we split the test dataset into segments, because each sample can have a different input-output ratio, that is, different memory and prediction length. Since we can't run sequences with different shapes together in one batch, we divide them into 5 segments based on their memory length. Each segment contains samples with the same memory length, allowing consistent and efficient processing within the model. So you can see here the start and stop means the start point of the where the memory length starts. So let's say we want to use the 100 steps of memory length, and it starts from 0 to 5. We use the start to be 0 and stop to be 5 so that we can just get the inputs with the same data length of the memory size. So we load the data set using our function, the get dataset. Then we load the model. You can see here the model STM we provide, trained by our LSTM model. And we go through the batches of the test data. Inside, if it's the first step, then we use an inH as is. Like the previous inH is known, then we can just use the inH value of the data, which is the first memory size. For the next steps, we roll inH and insert the predicted value at the end. You see here -1. So this mimics the autoregressive inference, where each prediction depends on the previous one, and stores the prediction values and measurement values. And you see we denormalize using the norm H, denormalize the results, and we can save it to the CSV files. You can see the predicted files and prediction files and measurement files in output folder in the GitHub. And all these values are just for plotting our results.
Hyukjae,
Yeah, sure.
can you go to the top of step 3 again? I just want to emphasize here in the definition of computing the total energy, right? We should emphasize what the units meaning of dB and H here means, right? The unit does make sense here in where since we're calculating the energy density, right? So we're taking the dB, which is in the units of volt per meter square, and we have the H, right? That's directly related to current, so that's in amps per meter, right? So technically, when we're calculating here is that we're calculating that instantaneous power at every single time step. So if you integrate B and H here, your units does make sense, right? The unit comes out to be power per volume, right? So it's PV here, which is that if you take V voltage over second square times the current over meter, right? That's VA over the cubic, which is what the volumetric loss is. So here, and then we sum up the entire testing sequence of this. So we are not doing the overall BH loops, but rather we're calculating for if we give you guys a segment of points, right? What is the total energy density for this segment specifically? There's no BH loop, since to complete the whole BH loop, you need a full sequence, and we're not testing the full sequence here. So here, this is what essentially the energy density we're talking about here means. And Hyukjae, we can add the comments to explain these and update it in the GitHub afterwards. So we will provide an updated version of this on the GitHub later to explain.
And also the slides. So just for your information, we're not doing BH area. We're doing VI sequence and integrating through the entire sequence for the loss. And we'll update the slides and update the code to make it very clear later.
Yep. And
Okay,
yep.
sounds great.
Please go ahead. Thank you.
Okay, yeah, great. I'll update it. Yeah, so the next step is after completing the inference, we have to save the outputs, use and also load the inputs from the data we have produced. Yeah, for sure you have to use your own path root here. And the file name, the first file, the padded file, as I mentioned, it contains all the input values of B, H, and temperature values. You should use this file to test your model. And this testing true file only gives you the ground truth value of the H sequence, so it's only for the evaluation. And because our models, the window size is 80 steps, we use the 80 steps, and the testing data set should be is 60 megahertz as that we provided. So we are using these values and use this function, we can get the predicted and measurement values of these H sequences. And as a result, you can see that this is iterating the 5 times. Like the H length here is the given memory length. So the first iteration, it gives the 100 steps, while the second iteration, it gives the 300 steps, which is the 30% of the total time steps. And so on, we have 500, 700, and 900. So this is just for the visualization of prediction results. You can see this is the memory length of 100 time steps, and from here 100 to 1000, we can see the predicted values, the red lines, and the measurement values, which is dotted blue lines. You can simply change the number up here, the M plot. Let's say like 80 here. And you can see the other predicted values. So there are like 0 to 104, which is 105 sequences here. And you can also find the NRMSE values of each sequences, like using these codes. And also the plot histogram of the NRMSE, so that your model works well or not, you can see from here. You can see also the average error and 95% error. Yeah, so this one is as we mentioned, the energy density given the time steps. So it's not the total time step. It's not the total core loss, but just an energy loss density per the given time steps, the 1,000 time steps. though the orange line is the measurement energy, while the blue line is the predicted energy. And we also can calculate the NRMSE of these core losses, the energy losses, using these codes. Oh, sorry. Yeah, so it's the end of our codes. And do you have something to add, Sky?
Yeah, one last thing about the format here. So this code is running on I believe here is running on local GPU, right? But it's using Jupyter Notebook. And the teams we've had a couple teams who have asked us if we can provide a Google Colab plan for training, because training may need larger GPUs, more high performance GPUs. And so the answer is yes, we are going to provide. If you are interested and you need a resource, we can provide you with a Pro plan, a Google Colab Pro plan, which yes, it will require a new Gmail account. So please email us and inquire about it, and then we will set up a new Gmail account, shared account with you, with the specific team, and we will give you that premium pro upgraded version of the Google Colab Pro using that new email account, and that way it's shared between us and the specific team, and you guys can access the better GPUs on Google Colab. And so please, if you have anything, please email us and inquire about the request, and we will give you the we will make the email address, and we will share it with you guys.
Yeah, and just the reason of doing this is just for us to cover the cost of the Colab account, and after that, feel free to change the passcode of the account, and we don't need that account, and we don't need to know what you're doing. Feel free to use that account as your own account. It's just easier for us to manage the budget. So we create an account, we pay for 6 months, Google Colab Pro, and then pass it to you. And we don't need an IP again.
Yep. And that's all.
Okay,
So
great. Yeah.
So Hyukjae, can
Yes.
you go to the GitHub website? Have you upload the files to GitHub?
Yeah, sure. I'll show you. So just a second. Can you see this site? The page?
Yes.
Okay. Yeah, you can see in this GitHub, the MagNet X GitHub, the tutorial file is here. And there are tutorial 1 and tutorial 3. The tutorial 1 is what Shukai did for the training process, and tutorial 3 is what we did today.
And tutorial 2 is on MagNet Challenge GitHub, and later we'll add all tutorials under the main GitHub repository. This is Shukai's own documentation.
Yes, that's right. And you can also see the tools here. Like I just added the save test for evaluation, the metadata file. So you can see this file later.
Maybe we'll reorganize that as well, so that people have a good idea on what is used for which tutorial here. So we might migrate that elsewhere.
Okay, yeah, that makes sense. Great. So if you see the evaluation file, the testing file here, you can see the same file, exactly same file as I showed. And you can go through it and see what see it and testing and evaluate your model, your own model. You can just simply change the model and and the network structure here.
So
All right,
just a little bit about the final test. What will happen in a final test is we'll first offer training data for 5 new material beyond what we already provided for the 10. And you can use the new training data to retrain your model or train new models from scratch or do whatever you want to do. And then we'll provide testing data for that 5 material in a format similar to what we have talked about today. So that's what's going to happen in the final test. So really between now and November, it's your time to play with the 10 material and you can do whatever you want. You can segment the data into your own training and testing, and then evaluate your method. Because in the end, this is a methodology challenge. We hope to find a method which will be useful for building a model for the new material. So that's how the final testing will be happen. So November 1st, you get new data, a set of new training data, and a set of new testing data for the 5 new material. So that's what we're going to expect. And the size of the data and the format of the data will be very similar to the 10 material we already covered. And the materials we will be offering for the 5 new material will be similar to the 10 material, but different material. Maybe we can go through the questions. Anyone in the attendee have questions? We'll be happy to answer any of them, or we can go through and discuss about the 5 questions in the Q&A session. Maybe Shukai, you can go ahead and maybe go over the 5 questions. Can you see the
Sure.
Q&A session? Yeah, you can
Yeah,
go
I can
ahead
see
and
it.
discuss about it.
Yeah, sure. So I'm gonna start with the first one, which is the deadline for submitting the proposal. The deadline currently for the 2-page proposal is June 15th. And that will be the 2-page proposal, just the initial proposal ideas that we are going to evaluate. It's not the most serious one. We just want to see what ideas teams are coming up with, and we
Actually,
will
we're
then
not.
evaluate.
In fact, we're actually not interested in what you're coming up with either. We are just interested in making sure everyone is ready. So you don't have to put your best ideas there. You can keep your best idea private. You can keep all your secret strategies. Just write something to show that your team understand the rule. That's all we need.
Right, right. Yeah. And then the second question is, are the given H and B waveforms still sinusoidal at a microscopic level? The answer is no. We are the overall, yes, we have a quasi-steady state excitation. The low frequency steady state excitation is not excited with pure sinusoid. In fact, it's actually mostly just a PWM type of waveforms here. So the excitations, however, has a magnetizing and demagnetizing segments, and they are odd symmetric. So it is steady state, but if you look at the A, B, or H waveform, neither of them are sinusoidal. And so this is not what a sort of a rigorous PWM, the PFC application is, but this is just how we excited the excited the system and collected our data. And so mostly it's trapezoidals and piecewise linear waveform here. So, and then the third question is there any correlation between the sequences of data? So no, there's no correlation at all. Every single full quasi-steady state sequence that we collect are completely independent. They're independent measurement. There is no correlation between any of these sequences. Although the excitation themselves, some of them are just same set of excitations, but different temperatures or different other operating conditions, but each sequence is collected completely independent and measured independently. So you should treat it as completely independent measurements there's no correlation between any of these data.
Right. There's a magnetizing and demagnetizing process between them. So every measurement we magnetize and demagnetize. So every measurement is a independent measurement.
Yes. Yes. And then the next question, the question is, for example, if we have material at like N49, there's no 7 frequency levels, but only 5 frequency levels. Then what are the 5 frequency levels? Well, we are not going to provide you exactly what the frequency levels is, because with the foundation model, we do not want to have that frequency level as an extra input, because we're supposed to be frequency agnostic. So to answer that question, you can treat that as a randomly sampled 5 frequencies. And the good model does not need the frequency as an input. So if you treat that as 5 completely random frequencies, your model should be able to, if it's good, it should be able to depict that sort of correlation in its own model without needing to see the frequencies. Because if you have a model, it should be able to use just the previous memory information to predict the future, right? And so if it's any arbitrary sequence, there's no such thing as frequency. It's just the data we provided has this frequency component in it, but as a model training or model creation, we did not include any frequency as an input. So so for that reason, you should just treat it as randomly sampled 5 frequencies.
And this implies some of the final testing philosophy. What we will offer is the training data set will be a uniform sampling of the entire operation space. And then we'll make sure that the training data covers the corners of the operating conditions that we're interested in. And then for the testing, it will be, again, it may not be uniform, maybe a just specialized sampling of the entire space, but we'll make sure that your model sort of see similar operating condition in the training data. We're not going to ask you to predict the material's behavior beyond what the training data is covering.
That's right. Yes. And the last question so far is there any tips for dealing with model predictions becoming unstable in recurrent prediction? So I'm assuming the autoregressive prediction here. So one thing that we figured is we have so far seen is that if you do a sequence to a scalar prediction and you're not training with many points, the autoregressive prediction can overfit quickly, because if you're training with very few or fewer data points, then rather than the whole database, which I believe you wouldn't have the space to anyways, if you do it so that way, sometimes the model can generalize, overly generalize towards whatever your training data provides. But your sequence may include many different points that are not seen in the training data. So then what happens is if you overfit, the autoregressive prediction overfits, then you may have a point where if there's an excitation that is very much so deviated from the training data, then suddenly it may diverge. Your prediction may diverge. So you have to watch out for maybe you don't need to train that many epochs to get the good result, but rather you should watch out for when does your autoregressive prediction overfits. And so one way to sort of fix this, or that we've seen that could have been better, is that instead of doing a sequence to point, right, to scalar, we have also done sequence to sequence. So with the sequence to sequence, because you're seeing the next future few points instead of just a single point. So the accumulation of error there is it's not big, so it can generalize well to the full sequence. So essentially you have seen the next few points already. And so it helps with stabilizing the prediction here. And so That's just what we have observed right now, but there can be many other strategies that could work. And
right. For example, you can do sort of physics informed machine learning and build some lossy mechanism in it so that if you have any random noise coming in, your system is still stable. But this we haven't honestly we haven't explored it. There are infinite way of doing this. You can go with a neural network structure. You can embed some analytical equations in there so that your model will always sort of predict something within the range that physics makes sense. So one limitation of data-driven methods is that you don't extrapolate. If anything go beyond your training data, you have to make reasonable judge. On the other hand, any analytical model cannot claim extrapolation capability without the data, right? So it's a chicken and egg problem. You can only verify your analytical model is correct in terms of extrapolation if you already have the data. But then if you have the data, maybe you can go with data-driven model, data-driven method because you already have the data. So that's an interesting loop that we find for this kind of data-driven modeling problem in terms of interpolation and extrapolation. But the other thing I want to raise is because MagNet Challenge 2, we're doing arbitrary wave. There are infinite combinations of excitations. So how do you actually sampling the data to create your own training data is a important technique. And this technique can be very useful in the future because a very good way of selecting or sampling the training data can lead to better wave measurement. Like we don't have to measure so many data. We just need to measure the data following the way that you create for training. So there are actually a lot of innovation space here compared to MagNet Challenge 1 because we are just dealing with a huge space for innovation.
that is right. Yes. We see one person, Xiaobing Shen raised his hand. I believe we can promote him to panelist. Hey, Xiaobing, how are you?
Hi, hello. Can you hear me?
Yes, yes.
It's okay. I just want to also discuss about the but I think Professor Chen at the last minute just explained that something that I'm interested to interpolation and extrapolation. It's all done. Thanks. It's well answered. Yeah.
Yeah, that's a question we ask ourselves. Like many people say analytical model can be used for extrapolation, and I put a question mark there because you have to verify with data.
Yeah, this is also what do we I do for the MagNet challenge 1. I'm also wondering since you already have data and what's the point? But thanks.
Right. I think this is the same question is true for every machine learning area. That's why machine learning is shaking the foundation of our physics model, because you claim your physics true because you have data. Then you have the data, you can train a data-driven model, which is also true. So
Yes. Great. Any more questions from the attendees?
I guess that's good. We're fast today. We're right on the 1 hour point. So if there's no more question, we'll end today's tutorial, and we'll update our slides and update our code because there are quite a lot of things that I think we can clarify. But feel free to let us know if you have any question. Testing is very, very important, and we haven't finalized our final testing strategy. Although what we're talking about today is more or less what we're going to do. But if you have any recommendation, any thoughts, let us know, and we're happy to try our best to make the evaluation fair and sort of have interesting enough, leaves enough space for innovation, and at the same time, we are really comparing models in a most comprehensive way. So that's our goal, and let us know if you have any thoughts or recommendations. Okay. So then that's all for today. Thanks everyone. We'll have one more tutorial session next Friday. And then where we'll more or less go sort of review what we have talked about as a full story and open the floor for discussion and Q&A.
Yep. Sounds good. Thank you, everyone.
Yep. Thanks everyone.